Alright, here's a complete sample titration of a weak acid. If you've been in lecture, you'll know that this type of problem is probably the most comprehensive and challenging that you will do in this entire unit. And the nice thing about titration of a weak acid or titration of a weak base is it's an excellent review for the entire chapter on acids and bases. There are several different types of calculations you use. So my recommendation would be that you give working out titration problems the first priority for this test. Not to say you ignore some of the other basic things, but this is a good place to start. So you of course need to know your strong acid so that you can identify whether or not the acid you're titrating is strong or weak. And in this case, hydrofluoric acid is a weak acid. Simply, it's not one of the 6 strong that you've memorized. A titration problem will typically ask you to calculate the pH before the titration begins, and that means simply what is the pH of the weakly acidic solution before you add any of the titrant. And then it'll ask you in increments what the pH is as you begin to add the titrant. Okay, so at some point, one of these amounts is probably going to be the equivalence point, the end point, when you've neutralized all the initial acid. And the last one is typically when you've added too much titrant. And so they're all solved a little differently. So let's go ahead and get started. Okay, before the titration, realize that there is only the weak acid or whatever we're titrating or the weak base present. Nothing else is present. And so think back to the beginning of the acid-base chapter. How would you find the pH of a weak acid? You can't just take the minus log of, because not all of that acid is going to release its hydrogen ions. So in any weak acid, we have an equilibrium if it's an aqueous solution, and the equilibrium is between its conjugate base. So we have some amount of hydrogen ion, but we also have some conjugate base and some intact acid. So this is an ice table. Okay, so I would say at the beginning, a rule to write down, if you like to do that when you study, is at the beginning of titration of a weak acid, it is simply an ice table, weak acid problem. Okay, ice table. All right, so, and obviously to do an ice table you need the Ka, and the problem did give us that. So let's go ahead and set up our ice table for this weak acid in equilibrium. Okay, and water is not going to participate, it's a pure liquid. And so the initial concentration of hydrofluoric acid is 0.3 molar. And the initial concentration of the conjugate acid in the hydronium ion is 0. And I'm going to call the change minus X for the hydrofluoric acid and plus X for the products. And so the equilibrium concentration of hydrofluoric acid is 0.3 minus X. Concentration of each of the products of the equilibrium is X. And so now I'm simply going to plug into my equilibrium expression for hydrofluoric acid and set it equal to the Ka. Here's the equilibrium expression and the Ka value, which was given to us. We're going to go ahead and plug in the values. So we set concentration of fluoride and the hydronium ion to X. Concentration of hydrofluoric acid was 0.3 minus X. Okay. You can actually solve this using the quadratic formula, and you probably should get practice using that. It will not be on my exam, but it probably will be on the final exam, which is ACS written. So, but in this case, since our Ka value is less than something of the order of 10 to the minus 3, we are going to neglect x, and so our equilibrium expression simplifies. Remember to show that you've neglected x for full credit on my tests. Okay, so then x squared equals 0.3 times Ka. Okay, and x squared equals, what is that equal to? X squared equals 0.000198. Oops. And the square root of that is, take the square root of both sides, 0.014. And what do we set x equal to? That is concentration of hydronium ion. Okay. The problem asks us for pH though, so now we have to find the pH of this. So pH is minus log of concentration of hydronium ion. And that equals pH of 1.85. Really, since the original problem only had 1 sig fig, if we were going to be paying attention to sig figs, it'd only be 1.9. Alright, so that's the pH in the beginning. Let's move on to part B that says, what is the pH when, how much did I say to add? 10 mils. All right, so now you have actually a chemical reaction involved. What is the chemical reaction? Anytime there's a chemical reaction, you want to write it out, okay? So we have hydrofluoric acid reacting with sodium hydroxide, and as in any acid-base reaction, the product is a salt, in this case sodium fluoride, and water. Alright, so clearly the pH is going to be affected by how much we have neutralized the acid we're titrating. So the first thing you want to do is a mole table. Once you start the titration, you want to create a mole table. And this is true for titration of strong acids or weak acids. You've got to figure out how much reacted. And so mole table, what we've been calling it, is a BCA table, before, change, and after. Okay, so let's see, how many moles of the hydrofluoric acid did we have before we started titrating? It was 0.3 molar. And how much of it did we have? Remember that molarity times volume will give you moles. We had 25 mils. So 0.3 molar times 25 mils will give you the millimoles of the acid. If you're uncomfortable working in millimoles, you can convert the 25 milliliters to liters and just work in moles instead of millimoles. That's fine. So 0.3 times 25. So initially we have 77.5 millimoles of the acid. How much sodium hydroxide have we added at this step? We've added 10 milliliters, and the sodium hydroxide was also 0.3 molar. And so we have 3 millimoles of sodium hydroxide to begin with, okay? And to begin with, of course, before the reaction, we had 0 of the products. Actually, water is not going to affect anything, so I'll cross it out. All right, so now, whatever, this sodium hydroxide is a strong base, so whatever you add, 100% of it's going to react with the acid, regardless of whether the acid is weak or strong. So this amount of sodium hydroxide is our change. It will all react. So we are going to subtract 3 millimoles because hydrofluoric acid and sodium hydroxide react in a 1-to-1 ratio. The same amount is going to be subtracted or reacted from both. And of course, because our products are 1-to-1, we're going to be adding 3 millimoles of the conjugate base or the salt of sodium fluoride. So what are our final mole values going to be? 7.5 minus 3. There are going to be 4.5 millimoles of hydrofluoric acid left. Sodium hydroxide will have completely reacted. It's a strong base. And what have we formed with this 3 millimoles of sodium hydroxide reacting? We have formed 3 millimoles of the salt, sodium fluoride. So here are our final mole values. And what you want to do with that is plug into Henderson-Hasselbalch. Why? Well, because you now have a buffer system. You have a weak acid, and you have its conjugate base. Because what is sodium fluoride really in aqueous solution? It dissociates in the soluble salt, dissociates into the cation and anion, and voila, this fluoride ion is the conjugate base of the original weak acid. So now we have a buffer. That will always be true throughout titration of a weak acid with a weak base until you reach the equivalence point. So now let's go ahead and set up the Henderson-Hasselbalch equation. So here's the Henderson-Hasselbalch equation. Remember that although the equation asks for the concentration of the conjugate base and the weak acid, it's okay to use the mole ratio because the liters in molarity cancel out. So you can use the mole ratio. That's usually a lot easier in a titration. Remember that the base, conjugate base, always goes on top of this ratio. That's a real common mistake to make, to flip that ratio. And so let's go ahead and plug in values. Formula for pKa is minus log, just like any p-value is minus log of the Ka, and the Ka for hydrofluoric acid is 6.6 times 10 to the minus 4. And the mole values we just got on our mole table for the conjugate base and conjugate acid, we found that we had 3 millimoles of fluoride and 4.5 millimoles of hydrofluoric acid left over. And so let's go ahead and simplify this equation. All right, so let's go ahead and simplify. pKa equals 3.18. Oh my God, if you hear heavy breathing, it's my dogs again. And let's see, 3 divided by 4.5 is 0.67. And the log of that is negative 0.18. So that kind of works out nicely. The pH is an even 3. Make sure that makes sense, okay? The original pH was 1.9. And so it makes total sense the pH has gone up a bit because we're adding sodium hydroxide. So that's great. So what can we summarize? How did we find this pH? How do we write a nice little summary statement about how to do that? Okay, so during the titration of a weak acid, that means once we've started adding the titrant, it's a two-step calculation to figure out pH. So the first step is to use a mole table to figure out how much is reacted. And the second step is use Henderson-Hasselbalch equation to figure out pH. once you have the mole ratio. All right, so keep in mind that during the titration, you're in what's called, before the equivalence point, you're in what's called the buffer region. Okay, because you essentially have a buffer. So let's move on to the next step of this problem. Alright, so we're going to solve this problem just like we did the last one. We've added some sodium hydroxide, we're in the middle of titration, and so we're going to follow the two-step calculation. And the first step, of course, is setting up the mole table. And so let's rewrite our reaction and go ahead and set up the mole table so that we can plug into Henderson-Hasselbalch. Okay, so the initial amount of hydrofluoric acid is going to be the same, and that was, as we calculated from the last step, 7.5 millimoles. We've added a little bit more sodium hydroxide, so you need to calculate how much of that. We have added in this step 12.50 milliliters, and it is a 0.3 molar solution, and so the millimoles we have of sodium hydroxide is 3.75. Of course, we have no sodium fluoride to begin with. And as the last time, sodium hydroxide is a strong base. All of it's going to react, so just take this amount of sodium hydroxide, it becomes your change. And of course, for every 1 hydrofluoric acid and sodium hydroxide that reacts, we produce 1 sodium fluoride, the salt. So that's plus 3.75. The final mole values for each of these, 3.75 millimoles of hydrofluoric acid left. All of the sodium hydroxide is reacted, and we have now created 3.75 millimoles of sodium fluoride. Remember that sodium fluoride is simply a source of the conjugate base, which is fluoride anion. So of course we have a buffer system again, and we'll use Henderson-Hasselbalch, but I want you to take a minute and look at the unique situation. We have equal amounts of the weak acid and its conjugate base present in our solution. That is called the halfway point in the titration. What does that mean? You might be able to visualize in your head what that means in the Henderson-Hasselbalch equation when you have equal amounts. But if you don't, I will show you on the next page. So what happens when the concentration of, or mole value of, the conjugate base and conjugate acid are equal to each other? Well, clearly that ratio equals 1. The log of 1 is 0, and so this entire second term in the Henderson-Hasselbalch equation drops out and is no longer important. And so for this step of the titration, which we call the halfway point, our pH is simply equal to the pKa. And I'm not going to go into, it's pretty easy in the beginning of a titration to figure out where the halfway point is. If you want to go ahead and do that, it may save you some time and effort, but I'm not going to go into it in this tutorial. So what was our pK? We calculated that on the last slide, and it was 3.18. Make sure that with each step, if you're titrating a weak acid, that your pH is going up a bit with each step, and it is. Our last pH was 3. So we are done. We're past the halfway point, and let's go on to the next step. So now we've added 25 milliliters of sodium hydroxide, and as far as we know, we're still titrating. And so we're going to go ahead and start solving this the way we have the last two problems, by a mole table and Henderson-Hasselbalch. It's going to be a little different, but we'll uncover that as we get going. And so doing our mole table first. Okay. So the initial amount of hydrofluoric acid, as in the last two problems, is 7.5 millimoles. Okay, and how much sodium hydroxide have we added now? Well, let's see. We've added 25 milliliters. The concentration is 0.3 molarity. And so we have added 7.5 millimoles of sodium hydroxide. What I want to point out this time is we've added enough sodium hydroxide at this point to completely neutralize the moles of weak acid that we have. What does that mean? Well, if we continue through with the mole table, that tells us that we will have 0 hydrofluoric acid left. Obviously, all the sodium hydroxide will have reacted also. And so what do we have present in solution? All we have present is 7.5 millimoles of sodium fluoride, which again is a source of the fluoride ion. So our initial weak acid is totally gone, and that's the definition of the equivalence point. Okay, when we have titrated or neutralized all of the initial acid or base that we're starting with. So at the equivalence point, it doesn't do any good to plug into Henderson-Hasselbalch. You no longer have a real buffer. You essentially just have the conjugate base, not the conjugate acid. So this is an entirely new type of problem. Okay, so how many different calculations do we have so far in this titration? Let's summarize for just a minute. Before the titration begins, we have an ice table, okay, of simply a weak acid, where we use the pKa and calculate pH. During the titration, we have a two-step calculation, where the first step is the mole table, and the second step is Henderson-Hasselbalch, okay, because we have a buffer system. What we've just discovered now is the equivalence point. At the equivalence point, all we have left is the conjugate base. Okay? So if this were titration of a strong acid and strong base, the pH would be equal to 7 exactly. But since it's a weak acid we're titrating, the conjugate base we end up with can react further in water and alter the pH. What is the equilibrium or reaction that the conjugate base can do? Well, in water, it can reform just a little, of the original weak acid. In the process of reforming that weak acid, it also produces hydroxide. That hydroxide is going to raise the pH. So since we're at the equivalence point, what is important to be aware of is that the pH at the equivalence point of a weak acid is greater than 7. Okay? That's only for titrating a weak acid. So to calculate the pH at this point, you need another ice table. But in this case, instead of using the Ka as you would for a weak acid before the titration, now we have a base, so we need Kb. So let's go ahead and go to the next page and work this problem out. Alright, so we need to recreate or to make an ice table, and we're dealing with a base at the equivalence point of titration of a weak acid, so we need Kb. And so let's go ahead and figure out what Kb is. Hopefully you remember that Ka times Kb equals Kw, which is 1 times 10 to the minus 14, as long as you're at 25 degrees, which we always are in our problems. And so Kb is simply Kw divided by Ka. 1 times 10 to the minus 14. The Ka for hydrofluoric acid given to us in this problem, 6.6 times 10 to the minus 4. So that means our Kb value is, let's see, 1.5 times 10 to the minus 11. We will need that for our ice table. And let's see, if we start filling in our ice table, we need concentrations, not moles. And something really important to remember, that during a titration, the concentrations are changing. Why? Because you're adding volume every time you add titrant. Okay, so during a titration, concentrations change, okay, because you're adding volume. So we need to figure out, we can't use the original concentrations. We've got to figure out what the new ones are. So that's the first thing we're going to do in the ice table. At the beginning of this problem, before we discovered we were at the equivalence point and we were doing a mole table, you may want to refer back, we found that we had created 7.5 millimoles of the fluoride ion. And so, since in the ice table we need concentrations, not moles, what is the total volume that we have from this titration now? Yipes. So you probably have to go back all the way to the beginning, and in that we started with 25 milliliters of hydrofluoric acid, and at this point we had added 25 milliliters of sodium hydroxide titrant. So our total volume at this point is 50 milliliters. And so at the equivalence point, the concentration of the fluoride ion, good thing I can cross out water, is, what does that give us? 0.15 molar. Kind of hard to see, but that's our initial concentration of fluoride ion. And as in any ice table, we're going to set the products equal to 0 in the beginning. Since we don't really know in an ice table how much of the equilibrium is going to proceed, that's what we're trying to solve for. We're just going to put minus x. And then, of course, on the product side, since they're all present in 1-to-1 ratio, these are both plus x. And so the final equilibrium concentration of fluoride is 0.15 minus x. Okay? And remember that Kb that we just calculated is 1.5 times 10 to the minus 11, which is very small. So it's very safe to neglect this x because the K value is so small. It's going to be very negligible compared to the 0.15 molar. So now we have equilibrium concentrations at the equivalence point. Let's go ahead and plug into the expression for Kb. Alrighty, we're almost done with this problem. So Kb, we calculated 1.5 times 10 to the minus 11. Combining the product concentrations and then divided by the concentration of equilibrium concentration of the fluoride ion. And so then x squared would then equal 0.15 times 1.5 times 10 to the minus 11. And that equals 2.25 times 10 to the minus 12, taking the square root of both sides, means that x equals 1.5 times 10 to the minus 6. What is x? It is concentration of hydroxide. So obviously don't forget your units too. But we still need to find pH, okay? So there are a couple ways to do that, and this is why it's a good review of the entire unit. We can go ahead and calculate pOH. That's one way to do it. So that would be minus log of the 1.5 times 10 to the minus 6. And let's see what that would be. So pOH is 5.82, and that means that pH is 14 minus 5.82, and that is 8.18. So that's the pH at the equivalence point. That matches with what we've learned. Remember I said at the equivalence point a weak acid will have a pH greater than 7. So that looks pretty right. That's awesome. There's going to be one more problem, and that's calculating pH when you pass the equivalence point. All right, I'm going to show you how to do this problem in a couple different ways. One is just the way we've been doing the others, and the other is kind of a shortcut. So we're going to start out by using a mole table to figure out how much of each of the species we have left. If you're not sure what to do, a good place to start is always a mole table. That'll tell you what your predominant or primary substance is in the titration. And so here we go. We've got hydrofluoric acid, NaOH, products, and we're going to go ahead and do our mole. Alrighty. So, of course, we started with 7.5 millimoles of the acid. At this point, we've added 26 milliliters of sodium hydroxide. The concentration of the sodium hydroxide is 0.3 molar. And so the millimoles of sodium hydroxide that we have at this point are 7.8 millimoles. Okay. So again, this is kind of a long, tedious way, but for those of you who maybe don't get it right away, it's a visual, but you don't have to go through this. So if we have 7.5 millimoles of acid and 7.8 millimoles of base, clearly only 7.5 millimoles of each can react. Okay? So you can't automatically subtract 7.8 because not all of it's going to react. Whoops, and I just started to do that. So 7.5, it's a limiting reactant, 7.5 millimoles will react. So you have none of the original acid left, which you would expect. You pass the equivalence point. You have some leftover sodium hydroxide. You have 0.3 millimoles of hydroxide. Okay? And you also have some of the conjugate base. You have 7.5 millimoles. This is an important point here. You have two bases, okay? At the equivalence point, it was important that we had some of the conjugate base present because that was the only species present. In light of the fact that we have hydroxide, which is a strong base, and fluoride is a weak base, we are going to ignore this. So the bottom line is past the equivalence point, all you care about is the excess base. So concentration of the pure hydroxide is all that you care about past the equivalence point. So remember that we have 0.3 millimoles of hydroxide left. So in order to calculate pH, we need the concentration of hydroxide, and we have moles here. Okay, so we have to divide by the total volume. What is the total volume at this point? Well, again, we started with 25 milliliters of the original acid, and we've added 26 milliliters of the sodium hydroxide solution. So the concentration of OH at this point, past the equivalence point, okay, is 0.3 millimoles divided by 51 milliliters. And so that concentration is 0.0059, capital M for molarity. Okay, so again, to get pH, I guess I would probably do POH first. So minus log of the concentration of hydroxide. And that gives you 2.23. So then pH would be 14 minus 2.23. And so our final pH is 11.77, okay, which you would expect. You've shot past the equivalence point, and so it's going to get rapidly more basic. That's it. I'm going to do one short additional problem after this to show you how to know ahead of time where the equivalence point is going to be. It's actually a reminder, and it's probably really important to listen to that because I'm sure there'll be a couple multiple choice problems that'll use this formula I'm going to use. So back at the beginning of the problem, we could have saved us some steps, and well, not really steps, but calculations, by knowing ahead of time where the equivalence point was going to be. And let me show you how to do that. So the problem told us that we had 0.3 molar hydrofluoric acid, and it told us that we had 25 milliliters of that. And we combined that with 0.3 molar sodium hydroxide, and let's say we want to know how many milliliters of that it would take to reach the equivalence point. Okay, so at the equivalence point of any titration, the following formula can be used. We went over this at the beginning of the unit, but it feels like forever ago now. And so that equation is this. I love this equation. It just saves, I think, quite a bit of effort. All right, so little a and little b simply mean how many hydrogen ions or how many hydroxides are in the substances you're working with. And in both cases, hydrofluoric acid only provides one hydrogen ion per molecule, and sodium hydroxide only provides one OH per unit. Okay, so let's just plug in. Molarity of the acid is 0.3. The volume of the acid we have is 25 milliliters. It does not matter the unit of your volume in this equation as long as the units are the same on both sides of the equation. So molarity of the base, 0.3 molar, and volume of the base is what we're trying to solve for. We want to know what this volume is at the equivalence point. So if you rearrange this equation, the volume at the equivalence point of base will be 0.75 divided by 0.3, and that is 25 milliliters. So 25 milliliters of sodium hydroxide will be the equivalence point in this titration. So why can that help you? That can help you because at the beginning of this entire problem, you would know in your head that at 25 milliliters is the equivalence point, and you can just start working the problem as you do at the equivalence point, which is to set up an ice table for the conjugate base. All right, that's it for this tutorial.